Okay. Remember the relationship between position, velocity, and acceleration. The derivative of position is velocity, right? So in other words, the slopes of the tangent lines of position is your velocity function. The slopes of the tangent lines of your velocity is your acceleration function, right? So with that being said, what if I just take one of those functions and look, what would the slopes of the tangent lines look like? Well, for example, in function A, if I were to put little tangent lines on there, isn't my tangent line always showing a positive slope on A the entire time? Now, positive means a positive value, so its entire derivative would have to be above the x-axis, wouldn't it? Are any of those functions above the x-axis the whole time? So can any of those be the derivative of A? No. So if none of those can be the derivative of A has to be which one? Acceleration, right? Okay. So that's one way to look at it. Now, B kind of has a combination of both positive and negative. C, negative, 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 negative. My tangent line is negative the entire time. So its derivative will have to be below the x-axis the entire time, right? So of the other options, which one is below the x-axis the entire time? B. Now, that could make this position and velocity or velocity and acceleration, right? I just know that it's the derivative. The last thing that I would kind of look at on this one is remember that for a function, a maximum or a minimum of a function will show up as a 0 in its derivative, right? So like a maximum on our position function showed up as a 0 of the velocity. A minimum right here has a horizontal tangent. Its derivative would have a 0 or hit our x-axis at that point. So I can see that this point corresponds to that point in A being the derivative of B. So with that being said, have we figured out the order then? B is the derivative of C because its slopes are all negative. B is completely below our x-axis. That point corresponds with that, so A is the derivative of B. Also, negative slopes, so below the x-axis. Positive slopes above the x-axis, right? So correct order, position function, C, velocity, B, acceleration, A. Okay.
So velocity B.
Yes.
B getting smaller at the end. Like isn't the velocity decreasing at the end? So how is the acceleration still increasing?
It's increasing right there. It's below our x-axis, but it's headed up.
But it's like it's negative. It's getting closer to 0.
Which is why this slope is getting less. This value is the slope of this line, not the slope of this line. The slope of this corresponds with this, and it's getting steeper, actually, as we get closer here than it was over here, which is why this is higher, because it's a greater positive value for the slopes. Again, I get it. The going back and forth between the position, the function, and the derivative, the function and the slopes, takes a lot of practice, which is why we're going to keep practicing it. Okay. With that being said, we're going to keep practicing it. I'm going to give you this situation. Now let me clarify. You are doing two completely separate problems right now. What you put as an answer in here has no impact. You're basically starting a whole separate problem here. They are not they're not related to each other. They are the exact same situation, but you're going to draw me a picture the first time as if you are drawing a position function that would represent what's going on then in this statement. A particle starts at 5, heads left for 3 seconds, then heads right for 2 seconds, stays still for 2 seconds, and then heads left forever. Then, completely separately from that, so like you never did this problem, you're going to do the second one. Same exact words, but you're drawing it as a velocity graph. What might help you is, again, that note sheet that we filled out that talked about when a particle is moving forwards or backwards, right and left. And what did that mean for our velocity compared to what did that mean for our position function? So I'll give you some time to think about that, and then I'll go through answers. Remember that time, seconds, would be your x-axis, right? Okay, if you're still drawing, keep drawing, but I'm going to kind of help a little bit off to the side here. When I'm thinking through this in terms of position versus in terms of velocity, right? If we go back to our note sheet and I wanted to talk about moving left compared to moving right, compared to standing still, by position, left, my position would be decreasing. Now, what does decreasing look like on a graph? That means some sort of a negative slope line, right, heading downhill. Right, my position function would be increasing or heading uphill, positive slopes. If it is standing still, our position function would be constant. And constant in a graph looks like a horizontal line, right? Now, compare that then to our velocity and what means moving right, left, and standing still in velocity. If we are moving left, our velocity function is less than 0 or negative. Now, in a graph, that means somewhere below our x-axis. That's negative values. If we are moving right, our velocity is something that is a positive value, and positive values are above our x-axis. And if it is standing still, our velocity function equals 0. In a picture, that would mean on the x-axis. Okay. So let's go back and draw our position function. It actually gives us a position to start with. It gives us that the particle is at 5 at time equals 0. So if I were to draw this picture, and we go, let's see. We start up at 1, 2, 3, 4, 5. So particle starts at 5 at time equals 0. It says that it will head left for 3 seconds. Left means my graph needs to be decreasing for 3 seconds. So starting at 0 up to 3, my graph is going to be decreasing. Okay? And then it heads right for 2 seconds. Right is going to be increasing. So for the next 2 seconds, my graph needs to head with a positive slope. Then it stays still for 2 seconds. Still in position is going to be a horizontal line. So 2 seconds, we have a horizontal line. And then it heads left forever. So for the rest of time, it needs to have a decreasing slope. Now, how far to go on each of those? We have no indication because they don't give us any other positions or how far left or right it moves. But you have to have the same slopes in those sections. And it didn't have to be straight lines. It could be curves, again. But you have to have, again, the same concepts covered there. So moving that then to our velocity graph, Okay. The place our velocity starts has no impact on our position. So although it tells us that it starts at 5, that really doesn't tell us where to start our position, our velocity function. But we do know that it is heading left for the first 3 seconds. Well, heading left means my graph needs to be below the x-axis for the first 3 seconds, right? So it's going to start below the x-axis, and up to 3 seconds, we will be below the x-axis. Then it heads right for 2 seconds, and right needs to be above my x-axis. After 2 seconds, it's going to be still, so by the end of this, I want to be back to my x-axis. So all of that is above my x-axis. That's all positive. Moving right. Then for the next 2 seconds, we are standing still, which means my velocity is a 0 slope or has a value of 0. So that would be along my x-axis. And then it heads left forever. So then for the rest of time, my graph is going to be below my x-axis. Negative values. Okay, so I did those completely unrelated. I did not draw one based off of the other. I just used the same situation to draw a graph based off of position, based off of velocity. Any questions for me on that? There is no rhyme or reason as to why I did linear. You could have done curves. As long as it had those same slopes in there, that's just fine. Okay? Or even a piecewise on your velocity graph would have been just fine. All right. Moving on. In this picture, we have a velocity graph. Always important to pay attention to what type of picture we're looking at. This is a velocity graph. And my question to you is, when is the particle represented in this graph speeding up or slowing down? So I'm going to give you some time to think about that. Go back to your notes from Wednesday if you don't remember what we look at to decide on speeding up or slowing down. But look through that graph and see if you can identify for me those intervals, speeding up and slowing down. Yesterday when we had a question about speeding up or slowing down, I think I drew a number line and kind of marked above and below our number line, or you could do that across your x-axis. Since we have a picture to look at, I could just kind of go across my picture and mark what's going on in each of those. So if I look at this as a velocity function, if you remember, speeding up and slowing down compares the value of the velocity to the value of the acceleration. When is it positive? When is it negative? In each of our different sections. And this one is really nicely broken up into clear sections as we go across here. Looking at this as a velocity graph, remember that it is positive anytime it is above the x-axis and negative anytime it's below the x-axis. So this is all positive velocities, right? Above our x-axis. These would all be negative velocities because they are all below our x-axis. And then it goes back to above our x-axis over here, positive again. Then if I change my view to looking at each of those sections and what the acceleration would be, I would look at it in terms of what is the derivative, what is the slope of each of those sections. And so as I look at this first section that would go from 0 to 2 is having positive slopes or heading uphill, its acceleration would be positive. From 2 to 4, it is a horizontal line, so it would have an acceleration of 0. The slope would be 0. The slope here, heading downhill, would be negative. The next piece would also be negative, heading downhill. This piece is heading uphill with a positive slope, and then a negative slope. Heading uphill again, that's a positive slope, and the last one would be a positive slope. And so then I can just kind of go piece by piece and say, okay, well, are they working together or working against each other? And so on that first section, I see that I have a positive velocity, positive acceleration from 0 to 2. You can use interval notation, you could use inequality notation. That graph would be speeding up. It's not doing anything right here as far as speeding up or slowing down because our acceleration is 0. Okay, so that would not be an interval that falls anywhere on those sections. The next piece that goes here, 4 to 5, we've got opposite signs, and that means it's going to slow down from 4 to 5. Our next section are both negative, from 5 to 6. That piece of graph would indicate that our particle is speeding up. Opposite signs, so going to slow down from 6 to 7. Negative, both negatives here, we would be speeding up from 7 to 8. Opposite signs, slowing down from 8 to 9. And finally, both positive from 9 to 10, speeding up. Any questions on the speeding up, slowing down question? No? All right. The last one, we're going to hold off on this because I wasn't able to get to it earlier. So we'll put this in. This is just a thing on your calculator that you can see that your calculator has a way to show you actually an object moving up and down, flight of an object on your calculator. So we'll save that for another day. You guys have your worksheet today is also your particle motion worksheet. We'll need a separate piece of paper to do this as well. Make sure that if you do have decimals, you are rounding to 3 decimal places.